Hey everyone, welcome to the second video in our series on the reactions of Chapter 9. In this video and in the video after, we're going to be talking about different ways of hydrating alkynes. Okay, so remember there's a lot of ways to hydrate alkenes. There is two ways to hydrate alkynes. Okay, so in this first video, we're going to be talking about acid-catalyzed hydration of alkynes, and then in the next video, we're going to be talking about hydroboration oxidation reactions on alkynes. Okay. So, as I said, in this video, we're going to be doing acid catalyzed hydration of alkynes. All right. So, the main thing that we need to know about this is that this is a Markovnikov reaction. All right, similar to the hydration, acid-catalyzed hydration of alkenes. This is a Markovnikov reaction. Okay. So other than that, there isn't really anything that we need to worry about too much as far as this reaction goes. So let's just look at a couple of examples. All right. So let's do this 3-carbon alkyne. All right. And what we do is we put this through HgSO4 on top, and then on bottom we have H2SO4. Okay, so we have this mercury sulfate salt, and then we have sulfuric acid. All right. And what this does is, remember in alkenes, we made alcohols, right? In this case, I'm not going to be making an alcohol, okay? I'm going to be making a Markovnikov carbonyl group, okay? So in this case, I'm going to make a ketone, all right? So all I need to do is use Markovnikov's rule, right? So if I'm hydrating something, then on this right carbon, that carbon's going to get a hydrogen because there's more hydrogens on the right, because on the left, there's 0 hydrogens, right? So on the left, I'm going to put my group, and then on the right, I'm going to put the hydrogen. So in this case, my group is a C double bond O, all right? So I'm going to be making a carbonyl group, all right? So carbonyl group is going to go on the more substituted carbon. So in this case, I'm going to make a ketone, all right? So let's look at another one. Let's look at this alkyne. So if I do this one, then again, similarly, I'm going to put the double bond O on the more substituted carbon. So that's this carbon, right? So the double bond O is going to go there. And everything else is just going to stay the same, basically. So I put a double bond O right here, and everything else stays the same. Okay. So that's all I'm doing. So you'll notice that I'm making ketones here. There is a way to make an aldehyde, and that's the only way that we can do that is with C double bond to, or C triple bond to C, right? Which is ethyne. So the only way I can do that is with ethyne. So if I react this with ethyne, then I'm just going to put, you'll notice that on the left side and the right side, both of these carbons just have 1 hydrogen on them. So they're equally, there's an equal amount of hydrogens on both. So Markovnikov's rule isn't really going to tell us anything here. So then I'm just going to be making a carbonyl group on 1, and there's a hydrogen there. So in this case, I'm making an aldehyde. So I made 2 ketones and I made an aldehyde. Okay, so this is the only way I can make an aldehyde with this reaction, because it's going to prefer to make a ketone if it can, right? So you'll see these terminal ones, I made ketones, and with this one, I make an aldehyde. But let's look at a internal alkyne, because these are all terminal. So let's look at an internal alkyne. So if we take a look at this internal alkyne, then you'll notice that again, on the right side and on the left side, I just have one thing on each, right? So there's no hydrogens on this alkyne. All right, so since there's no hydrogens on this, or hydrogens directly connected to the C triple bond C, right? So Markovnikov's rule isn't really going to apply here, right? So again, same reagents as last time. So in this case, I could make this, right? Like, because I could put the carbonyl group on this carbon, or I could put the carbonyl group on this carbon. Well, let's take a look at this. These two are actually the same thing. these are the same thing. If I just rotate this and flip it, then they both become the same thing. So I just get one product here. So this is a internal symmetrical alkyne. So if I have an internal symmetrical alkyne, I just make one product, okay? Because these two are equal to each other if we just rotate them, all right? So now let's look whenever we don't make just one product, all right? So let's do one example like that. So if I take a look at this one, this is unsymmetrical, right? You'll see this one was symmetrical. The left and right side were the same. On this side, that's not, on this one, that's not the case, right? So here I can put the carbonyl group on the left of this, or I can put it on the right. So if I put it on the left, then I'm putting it on 1, 2. I'm putting it on carbon 2. And there's 5 carbons in this total. So 1, 2, 3, 4, 5. So I can put this on carbon 2. Or I could put this on 1, 2, 3, carbon 3. So 1, 2, 3, 4, 5, and 3 is in the middle. So in this case, I make two different things because it is an internal alkyne that's unsymmetrical. It's an unsymmetrical internal alkyne. So that means that I have the possibility, since both carbons are equally substituted, then I have the possibility of making a C double bond O on either one, okay? So this is pretty much everything you need to know for this reaction as far as just making products goes. So I either make a ketone with terminal alkynes, or I can make an aldehyde with ethyne. And then with a symmetrical internal alkyne, I make just one ketone, but with an unsymmetrical internal alkyne, I make 2 ketones, okay? Make 2 ketones. So other than that, there's not really any other variations on this reaction at all. So I think that we should just take a look at the mechanism and then call it good. And the mechanism I'm going to be doing is for this. Okay. So, and we know what this makes as well. Let me write the product. All right, so that's our product. Okay. So what's happening here is that the first thing that's going to happen is this HgSO4 is a salt. It's soluble in water, right? So this is going to dissociate, and it's going to make just Hg2 plus ions. So I'm going to write those here. And this is very similar to the oxymerc alkene mechanism, if you remember that one. So this is going to make Hg2 plus. So I'm going to start with Hg2 plus. And similar to oxymerc, the Hg is going to get attacked by the triple bond, and this is going to attack the triple bond back. Okay, that's going to be the first step. So then what that gives me is it gives me a 3-membered ring. So on one side, I have a methyl group, and then on this other side, I have a hydrogen, right? So I'm not going to draw it. But then I have Hg here, right? And then I also have this other bond here that I haven't used, right? So let me draw that a little bit more clearly. I have this other bond here that I haven't used. So I just use one bond in order to make this ring structure, okay? And then this mercury is going to still have a 2 plus charge, okay? It still has a 2 plus charge. Okay, so now that I've made this ring structure, what's going to happen is water, so H2O, and water is going to be there just because I have H2SO4, and that's going to be dissolved in some amount of water. So water is going to come in, and it's going to attack the more substituted carbon and break this bond. And carbon will always attack, or not carbon, water will always attack the more substituted carbon. Okay, that's always going to be the case. That's why we get a Markovnikov alcohol in this reaction. Okay, so just to be clear. Okay, so then I have this, and my mercury is over here. It now has a +1 charge. And then I have water that I just added, which has a +1 charge. Okay, and then I also still have this double bond here, right? So double bond has not left yet. Okay, so now I need to deprotonate the water, right? I always had to have this step basically. So we're very familiar with this step, deprotonating waters. That's no problem. So we deprotonate the water. So then that's going to give me OH. And it also gives me H3O plus. Okay, so now what's going to happen is something called a keto-enol tautomerization. Okay, so from here to here, I'm going to have a keto enol. Okay, so keto and then enol tautomerization. So keto enol tautomerization. And what this means is that something called a enol. Okay, so this is an enol. All right, so think about that. Enol. En refers to a double bond. Ol refers to an alkene. So en, I have my double bond, and coming off the double bond is an alcohol. So it's literally an enol. All right. So an enol is turning into a keto group. Okay. So a keto group is a carbonyl group. All right. So that means that this enol is going to become a carbonyl group. And we don't need to worry about how this happens necessarily. I'll draw it out later, but we don't need to worry about it for right now. So all that's going to happen is this double bond is going to go here, turn into a carbonyl group, and then I lose a hydrogen basically. So I formed this carbonyl. All right. And that's my keto-enol tautomerization. All right. Okay. So now what happens is I have acid in solution, right? Because I have H2SO4 in solution. So I have some H3O plus in here. And what's going to happen is the H3O plus is going to protonate my alcohol on my carbonyl group. So then that's going to give me this. So that gives me a protonated carbonyl. Oh, not two, sorry. Just one. So protonated carbonyl with a positive charge on it. And then I get water as well. Okay. So now this protonated carbonyl, what's going to happen is we're trying to get rid of this mercury. Okay. We're trying to make sure that this mercury is gone eventually. So what's going to happen is this bond here is going to go here to form a double bond. Okay. So we're going to form a double bond there. And then these electrons here are going to, that were originally in this double bond, are going to go up here onto this oxygen. So that way I can get rid of the mercury and I can get rid of the charge on the oxygen at the same time. Okay. So both of those things are going to happen at the same time. Okay. So now what that leaves me with is a double bond here, and I have an OH group now. And then Hg2 plus just left, right? Hg2 plus just left. So now I have an enol again, right? This is an enol. So you guessed it, I can go through a keto-enol tautomerization again. So let me write the keto-enol tautomerization. I'm just going to say tautomerization. So I have a keto-enol tautomerization again into the ketone. That's it. So then I get my product, right? I get my acetone out of this. So I have two tautomerizations in this mechanism, but yeah. So it's similar to oxymerc, but it's not exactly the same. All right. So, okay. So I think that it may be just a little bit helpful to look at the mechanism of a tautomerization, all right, it's not bad, right? It's really not bad. So for the tautomerizations that we're looking at here, what I'm going to do is just go over here, and I'm just going to very, 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 very quickly talk about a tautomerization. Just so we have some baseline understanding of tautomerizations. So for these were acid-catalyzed tautomerizations. So I'm just going to take the enol that we had, right? So we have this enol here, okay? And then in the solution, there was acid, right? There's acid in the solution. So let's draw H3O plus here. Okay, this is going to be short, so. Okay, so this here, one of these electrons on this oxygen are going to go down here and form a double bond, a C double bond O, okay? But at the same time, since that would give this carbon 5 bonds, this double bond has to break. So this double bond is going to take a hydrogen off of acid, off of hydronium. And then that gives us this, and this is a protonated ketone currently, right? Protonated acetone. And this also gives us water, right? H2O. So now what's going to happen is another water is going to come in, and it's just going to take that hydrogen off and put those electrons on there, and then I'm done. Okay, so then that just reforms my hydronium. Okay, so it's, again, acid catalyzed, so the catalyst is constantly reforming, right? So this is what the acid catalyzed tautomerization looks like. So all that I'm doing is taking the enol and it's forming the carbonyl group, and then taking a hydrogen off of acid, and then I have a protonated carbonyl, which eventually gets deprotonated, and then I just get my regular carbonyl group. Okay, so if we go back to look at the other mechanism here, right? So in this mechanism, then I'm having that tautomerization happening here, right? So this is forming a carbonyl, and then it's taking a hydrogen off of acid, and then water is coming in here and taking this hydrogen off, and then I get this, right? And then finally, we drew the tautomerization of this to this over here. Okay, so between this and this, I'm getting this going on, all right? So just so we kind of know what's going on with tautomerizations. All right. So I think that that's everything for this video. In the next video, we're going to be talking about hydroboration oxidation of alkynes. So I appreciate you watching this video. Hopefully it was helpful, and I will see you in the next one.